So for around 200 years in physics, it was a well-accepted theory that light was a wave. Isaac Newton had suggested otherwise, but thanks to the work of Thomas Young and Christian Huygens, it was well accepted for over 200 years that light was in fact a wave. However, at the turn of the 20th century, the early 1900s, there was a series of experiments relating to the photoelectric effect, or called the photoelectric effect, that provided observations that completely disagreed with the wave theory of light. And that's what I want to explain today in general, and how one particular physicist managed to resolve this theory and came up with an entirely new theory that explained things perfectly. So what was the photoelectric effect? So basically what physicists observed was that if I had a metal surface of some metal like sodium or cesium, and I shine light on it or irradiate it with some radiation, as we knew that at that point in time that light was an electromagnetic radiation, then it would release some charged particles. They found out that these charged particles were in fact electrons because they managed to observe a current flowing. And this current, we know that current is the flow of electrons, so this means that the light actually led to the release of electrons. And then they started doing different things. They started playing around with the intensity of the light that was used, and they started playing around with the frequency of light that was used as well, right? And they saw that when they increased the intensity of light, the energy of these electrons didn't vary. And they measured this energy using the potential of the plates in a cathode tube. And they saw that this potential that is stopping the electron, we called it a stopping potential or a negative potential, did not change with the intensity of the incident light or the incident radiation. And they knew that by a law of conservation of energy, that the energy that the electron possesses, which was purely kinetic energy, is in fact equal to the charge of the electron into its stopping potential. So the kinetic energy of the electron, that is K, is equal to the charge on the electron E times some potential V. And the experiment showed that the intensity didn't affect this V. So V didn't change if I changed my intensity, which meant that my energy didn't change if I changed my intensity. However, according to the wave theory, my energy should have increased if my intensity of light increased, right? And another thing they saw was this potential and frequency were directly proportional to each other. So the higher the frequency, the higher was this potential, or the stopping potential, the value of the stopping potential, which means the higher was the frequency, the higher was the kinetic energy. Nobody seemed to understand where exactly or how exactly to explain this. Until 1905, when Albert Einstein came about with his theory on the photoelectric effect. Now Einstein made use of Planck's theory. Planck, or Max Planck, was a German physicist who in 1900 suggested that energy is made up of discrete units called quanta. Now what are these discrete units? Well, in a very simplified manner, a discrete unit or a quanta is a packet of energy. So if you like to think about it, then this is an easier way to imagine a water bottle, and you know that that water bottle can only contain a certain amount of energy, right? Similarly, a quanta is like that water bottle. So if I asked you what was the water carried by, let's say, 10 water bottles, you just, of all of the same type, then you just tell me that the total water is the number of water bottles times the water carried by each bottle. Similarly, the energy of each quanta, according to Planck's theory, was some constant h, which was Planck's constant, into the frequency of the incident radiation, h times f. And the total energy carried by the radiation was the number of these energy quanta into the energy carried by each quanta. Now Einstein made use of this to explain the photoelectric effect, right? So let's go back. I have a metal surface, right? And I have some incident radiation that's falling on this metal surface, and there are electrons that are being emitted by this metal surface. So now Einstein said that, hey, let's not consider this light to be a wave. Let's say that this light is actually a collection of particles. So in these particles he termed as photons. So he said that each photon has some energy by Planck's theory, which is h times f, right? And because there are so many photons, the total energy will be h times f into the number of photons, right? So these photons carry the energy and they transmit it to the electrons on the metal surface, and the electrons move, and so I observe a current. Now, how did this explain the theory? Well, Einstein didn't just say this. What he managed or actually said was he came up with this nifty little equation. He knows, or the experiment proved, that the electrons only carry kinetic energy because they're moving, and any moving body carries kinetic energy, right? And this kinetic energy is equal to the incident energy of the photon or of the electron, is the incident energy that it takes minus some minimum energy that you need to supply for an electron to be released. And this minimum energy is what they found from experiment, and that's why he came about with this particular equation. So now this explains a few things, and this minimum energy he termed as the work function, and this work function, according to experiment, depends only on the type of metal surface. So irrespective of where I get my metal from, the work function for some particular metal, say sodium, will stay the same. Irrespective of whether I get it from Asia, I get it from Australia, I get it from Europe, the work function is going to be the same. So that means that my kinetic energy, which is the difference of this term minus a constant, is only going to depend actually on this term, and this term depends only on the frequency, because Planck's constant, as you know, is a constant. So that means the kinetic energy depends only on the frequency, which was the experimental observation that was seen in the photoelectric effect. Wow, now that's cool. Now what else? I know that, the kinetic energy has to be positive. This is what classical physics dictates, right? So that means this quantity mathematically must have a value that is greater than 0, right? So HF minus this work function must be greater than 0. So let's add this phi to both sides, right? So you're going to get something like this. I'm going to get HF is greater than phi, right? So if HF is greater than phi, I can divide by H on both sides. So I'm going to get my frequency, that is F, is greater than some phi over H. So, let me write that more clearly, that this frequency is greater than phi over H. And this phi over H is a constant, because I know for a given metal, I know the work function is a constant, the Planck's constant is a constant, so my frequency needs to be greater than some constant value of frequency, and I know this is then some constant value of frequency, right, F0, called a threshold frequency. And this is also something, and this frequency will also correspond to some energy, right? If I were to, now because I know that F0 is phi over H, I know that phi, right? Because I know that F0 is phi over H, I know that phi is nothing but H times F0, which means I need to supply some minimum energy, which explains what I had observed in my experiment. So Einstein's theory corresponds to that as well. Now what about intensity and energy? So Einstein said intensity is the number of photons that fall on a given area in a given interval of time. So more number of photons means that each photon carrying some energy, so more photons would imply they carry more energy, so they could distribute energy to more number of electrons, so more electrons would gain sufficient energy to come out of the metal surface, and I know that more electrons would mean more current, so higher intensity implies a higher current, right? And what about the stopping potential and frequency relation? Well, that too. Remember when we figured out that the kinetic energy is actually the product of the charge into the potential of that particular plate that was used in the experiment? Well, let's just plug that value in here. What you basically see is this, E times V, right? We know that kinetic energy is E times V according to our experiment, is equal to the frequency minus this work function. So if I were to divide by the charge of the electron on both sides, I would get this. And now this is a constant and this is a constant, and this equation is of the form y is equal to mx plus c, which is a straight line, which is exactly what I had observed in my experiment. So my experimental observations corresponds with Einstein's theory, and the slope, and basically so that means I have a potential versus frequency graph, which is a straight line, and the slope of this line is h over e, which is m, right? And that has to be a constant. So irrespective of the metal I choose, I should have a constant slope if I plot a graph between the potential and the frequency. This was actually proven by the American physicist Mulliken when he tried to disprove Einstein, and he rather landed up making Einstein's theory more resolute. But this created an obvious problem, and even Einstein realized this. If light behaves as a particle in this situation and as a wave otherwise, When does light decide to say, hey, I'm not going to behave as a particle, I'm going to behave as a wave? Nobody really knew this fact and nobody could really digest it until de Broglie came up with this hypothesis in 1924, where he said not just light, but all matter exhibits this wave-particle duality, and the wavelength of this matter is given by Planck's constant divided by the mass of that matter into the speed with which it's traveling. Lambda is equal to h over mv. And because of this theory, de Broglie opened up the field of what we know today as quantum mechanics. And the idea, without quantum mechanics, you wouldn't have ICs and chips, and you wouldn't have computers and these fancy gadgets and phones that we have today. But it's interesting to note that the whole idea, or the whole field of quantum mechanics, came about because Albert Einstein tried to explain this photoelectric effect, and landed up opening an entirely new branch of physics as we know it.